Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing unit number 9, lesson number 2 on inscribed angles. Now remember, this unit is all about the geometry of a circle. And an inscribed angle is a particular type of angle that shows up in circle geometry. It's an important type of angle, and so we should right away get into what it is exactly. But then we'll see how it relates to the arcs that we introduced in the last lesson. So let's jump right in and learn what an inscribed angle is. It's pretty easy. An inscribed angle is any angle that has its vertex on the circle and its two rays intersect the circle. All right, and that's kind of important because you could easily have an angle, right? You could easily have an angle, a circle, and some vertex, and like this, but that would not be an inscribed angle. Even though its vertex is on the circle, an inscribed angle is one where the vertex is on the circle and then the two rays intersect the circle. Okay? So let's take a look at exercise 1 right away, where we've got a circle, we've got lots of angles, etc. Exercise number 1. In the diagram below of circle O, various points on the circle have been shown. Letter A, name two inscribed angles and the arcs intercepted, also known as subtended, by the angles. Okay, so let me do one and then you do another one. So remember, an inscribed angle has to have the vertex on the circle, okay, and then its rays must intersect the circle. So a good example of that would be angle DAC, okay? Angle DAC is an inscribed angle because its vertex A lies on the circle. Now, the arc that it intercepts, or subtends, is this arc. All right? So it intercepts or subtends arc CD, and it's very important that you can see that, all right? Then it's pretty easy, right? You simply look at where the two rays intersect the circle. Those 2 points will be labeled, and the arc that's in between them is the arc that is subtended, intersected, or intercepted by that angle, all right? So let me go back to the thinner line, and I'm going to say arc CD. All right, why don't you go ahead and name another vertex angle and the arc that it subtends. All right, well, there's a few different choices here. I'm going to go to red so that we can see it a little bit better. And I'm going to go with angle ABD. All but done. Angle ABD is an inscribed angle, and the arc that it subtends is arc AD. Now, there's other inscribed angles, okay? There's angle ACD. That would be another inscribed angle. There's angle CAB. That would be another inscribed angle. As long as the vertex lies on the circle and the two rays of the angle intersect the circle, it is an inscribed angle. Letter B, very important. Can two inscribed angles intercept or subtend the same arc? Can they? And the answer is absolutely. Okay, there's just no question about it. In fact, I can give you a great example in this picture, right? The angle that I just drew, angle ABD, intercepts or subtends arc AD, but so does angle ACD, right? So let me go green. Angle ACD also intersects that same arc. So the answer here is absolutely. Absolutely. And again, it kind of makes sense. I mean, if you think about it, if I took a circle and I just put 2 points on it, let's say A and B, and then I chose a third point over here, C. Well, that angle, that inscribed angle, intercepts arc AB. But then if I took another point over here, D, and I intercepted that, then that would also intercept that. Doesn't have to just be 2. We could have point E down here, and that inscribed angle intercepts that arc. So yes, absolutely. And that's important. So let's talk about the inscribed angles and the arcs they intercept. The measure of an inscribed angle will always be half the measure of its intercepted arc. Wow. And again, remember, the measure of an intercepted arc the measure of any arc is really just the measure of the central angle, right? Remember central angles, right? So let's just take a look at this theorem, okay? And it is a theorem, we'll prove it in a little bit. But the measure of angle C, or ACB, is 1/2 the measure of arc AB. Again, keep in mind, right, what I'm really saying there is that that's 1/2 of the measure of angle AOB. Remember, we always talk about the degree measurement of the arc as sort of like how far around in terms of degrees of the circle that arc represents, and we think about that in terms of the central angle that's made or that intersects that arc, okay? And this is amazing. I mean, it's really phenomenal that no matter what, right, no matter what, that inscribed angle will always be half of the measure of that arc. This is one of those wonderful things that you can really see nicely in GeoGebra. All right, let me extend my page a little bit so that we can get it all the way on the screen. Well, maybe not all the way on the screen. Anyway, let me make this circle just a teeny bit smaller. There we go. So here we are, right? And again, it's hard to get these angles to be beautifully nice, but here I've got an angle that's just about 120 degrees. And notice this inscribed angle has a measure that's just about 60 degrees. And what's cool about this is, again, you know, no matter where I move this, let's say I try to get it up close to a 90-degree angle. Oh, there it is, perfectly a 90-degree angle. Look, now the inscribed angle is 45 degrees. Remember how we were just having that discussion about could an inscribed angle, or could more than one inscribed angle intercept the same arc? Well, watch this. As I move D around, no matter where I put D, it consistently is 45 degrees because it keeps intersecting that arc that is 90 degrees. Whoops, that I didn't mean to have happen. That's okay. There we go. So this is an amazing phenomenon, and it's one of the first really, really important facts about circle geometry that you have to memorize. You really do. An inscribed angle is always 1/2 of the arc, or the measure of an inscribed angle is always 1/2 the measure of its intercepted arcs. Okay? And we're going to eventually go on and prove this. Okay? And we're going to start by proving it for a very special case. Before we do that, though, we have to review a theorem that we haven't seen for a little while. It's called the exterior angle theorem. Now, we've used this a few times, but recall what the exterior angle theorem says. The measure of an exterior angle of a triangle is equal to the sum of the two remote interior angles. So again, remember how this works. I've got some triangle, and if I take a side like BC and I extend it out to some other point, call it D, whatever, it creates an exterior angle. Now that exterior angle is adjacent to one of the interior angles, but more importantly, that exterior angle is the sum of the two angles it's not adjacent to. So that thing is angle 1 plus angle 2. That's going to be pivotal in the proof that we're about to do. All right? And again, this is going to be a very simple proof. It's not going to be any kind of T-table or anything like that. So let's take a look at an example where we have an inscribed angle A, or BAC, but this is a special case. Specifically, AC is a diameter, okay? So we have a very specific case here. This isn't the general case, but a specific case where AC is the diameter. So I'm gonna prove right now that the measure of angle A is 1/2 the measure of arc BC. Let's take a look at that in this problem. Exercise number 2. In the diagram of circle M, AC is a diameter. We wish to show that the measure of angle BAC, which is the same as, angle 1, is equal to 1/2 the measure of BC, right? So just to be clear, This is also the measure of angle 1. Okay? Now, letter A asks us, why is triangle BMA isosceles? And what does it tell you about angles 1 and 2? Think about this for a minute. All right. Well, what do we know? We know that AM is congruent to BM because both are radii. All right? And that's why it's an isosceles triangle. Right? It's an isosceles triangle because this side and this side are congruent. Simple enough. Okay? Now, what does that tell you about angle 2 and angle 1? Well, it tells us the measure of angle 1 equals the measure of angle 2. And that's base angles are equal in an isosceles triangle. All right? So I know that angle 1 and angle 2 are equal. Based on A, why should the measure of angle BAC be 1/2 of arc BC? Pause the video now and see if you can figure this out. All right. Well, this is why. By definition, the measure of arc BC is equal to the measure of angle 3. Okay? Because angle 3 is a central angle, so the measure of arc BC and the measure of angle 3 are the same thing. It's by definition. Okay? Now, the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3. Right? That's the exterior angle theorem right there, right? Angle 3 is an exterior angle of triangle BAM or BMA, right? So that angle 3 must be the sum of 1 and 2. But that's also the measure of arc BC. And yet, 1 and 2 have the same measurement, right? That's from letter A. So I could just say 2 times the measure of angle 1 is equal to the measure of arc BC, right? Because both of these are equal to the measure of angle 1. And therefore, the measure of angle 1 is 1/2 the measure of arc BC. And that's what we wanted. Okay? Now again, you might say, well, yeah, okay, sure, great. So it works in this case. In other words, I could say, all right, if I've got an inscribed angle where one of the two rays is a diameter, then the measure of the inscribed angle is 1/2 of the arc that it intercepts. But that's a very specialized case. The vast majority of times, inscribed angles aren't going to have one of the two rays being a diameter. So now let's extend it to basically all types of inscribed angles. Let's take a look at the exercise 3. Bring this back in frame a little bit more. Let's take a look at what it says. In the diagram below, we wish to show that the measure of angle BAC is 1/2 the measure of arc AC. All right? Actually, we want to show it that it's 1/2 the measure of arc, my apologies, BC, not arc AC. I don't really care about arc AC at all. Okay? So again, we're trying now to prove the theorem in a way more general way. So I've got inscribed angle BAC, and I want to show that it is 1/2 the measure of arc BC. 1/2 the measure of arc BC, not AC, no matter what typo I have up there. Okay, one thing that I've done is I've drawn in a diameter that starts at A, goes through the middle of the center, or the center of the circle, and out to D. Okay, and we'll see why that is. Letter A says, based on exercise number 2, what can we say about the measure of angle BAD and the measure of angle DAC? Think about that for a minute. Well, we can say that the measure of angle BAD, right, which is, this inscribed angle, is 1/2 the measure of arc BD. Okay, because this is exactly the scenario we just looked at. In exercise 2, we proved that for an inscribed angle where one of the two rays is a diameter, then the measure of that inscribed angle, BAD, will be 1/2 the measure of the arc it intercepts, in this case BD. But we can say the same thing about the measure of angle DAC. That's also 1/2 the measure of arc DC. All right? So again, that's that same case from exercise number 2. I've got one ray, and then I've got the other ray, which is a diameter. All right, so we've already proved for those special cases. Now, letter B says, using your answer from A, algebraically prove that the measure of angle BAC is 1/2 the measure of angle BC, or measure of angle of arc BC. You'd think I would have caught it the second time, I didn't. All right, well, how do we do that? It's kind of cool, right? We can say, using the addition property of equality, that the measure of arc BAD plus the measure of angle DAC is equal to 1/2 the measure of arc BD plus 1/2 the measure of arc DC. Okay, so all I did was add these two equations together. That's called the addition property of equality. Okay, you can add two true equations together anytime you want and get another true equation. But BAD plus DAC, well, that's the measure of angle BAC. That's simply the whole is the sum of its parts, right? When I add this angle, this guy, to DAC, this one, I get the angle I care about, BAC. All right? Now, what do I do with this? Well, I'm going to factor out that 1/2. Okay, and I'm going to get 1/2 the measure of arc BD, whoops, plus the measure of arc DC. But if we add arc BC to arc DC, then we get arc BC. So we can now say that the measure, whoops, sorry about that, the measure of angle BAC is equal to 1/2 the measure of arc BC. Okay. And that more or less proves it in general. There's actually a third case, but we're not going to get into it right now. You'll see it on the homework. Okay? But this is the more generic case. Right now we've just got this generic BAC, and its measure is 1/2 the arc BC. That is an amazingly important theorem. So let's apply it. Okay, let's take a look. Exercise number 4. In circle O shown, the measure of angle MOP, MOP, is 118 degrees. Explain why the measure of angle MNP equals 121 degrees. All right, this is kind of cool. All right, pause the video now and see if you can figure out why the measure of angle MNP must be 121 degrees. All right, well, let's go through it. Based on the fact that the measure of angle MOP is 118 degrees, that means that the measure of arc MP must also be equal to 118 degrees. All right, so this arc MP or MNP, doesn't matter which, that arc also must be 118 degrees by definition because this is a central angle. But that means, let me actually move my little m down a little bit. That means that the measure of arc MQP, the major arc, is 360 degrees minus 118 degrees. Bring my handy dandy calculator up. 360 minus 118. And that means that the measure of arc MQP must be 242 degrees. All right, so far so good. But the measure of angle MNP must be 1/2 of the measure of arc MQP, right? Because this angle, let me do it in green, I think it'll help. This angle that we care about, MNP, intersects this arc. right? And it must be therefore 1/2 of its measure, which is 1/2 of 242 degrees, which is 121 degrees. All right, but notice how many different things we needed to use there, right? First fact we needed to use was the fact that the measure of an arc is equal to the measure of a central angle that intersects it. The second thing we used is the fact that when we add a minor arc to a major arc, their sum must be 360, so to figure out the measure of a major arc, we're going to do 360 minus that minor arc, giving us the 242. And the final thing, of course, is what we just looked at, which is that the measure of an inscribed angle will always be 1/2 of the measure of its intersected arc, 121. All right, let me step out of the way. Go ahead and write down anything you need to. All right, let's do it. One more problem, or a couple more problems, whatever. Exercise number 5. In the diagram of circle K shown below, RS is a diameter. That's important. Diameters are important. And the ratio of measure of arc RT to TS is 2:7. Determine the measure of angle TRS. All right. So, what I always like to make sure I'm doing, especially in circle geometry problems where the diagrams can be quite confusing. This one's not too bad. We're going to get to some that are horrible. Well, maybe not horrible, but they're pretty complicated. Is I want to make sure I understand which angle I'm trying to calculate. I want to know the measure of angle TRS. All right, now that's an inscribed angle, TRS, which means what I really ideally want is I want the measure of arc TS. All right, I need to figure out the measure of that arc. Now, what I was told though, is I was told a ratio between the measure of arc RT and the measure of arc TS. I was told that the ratio of the measure of this arc to this arc is 2:7. All right? So if I had like 20 degrees, 70 degrees, right, then that would be 2:7. Or if I had 2 degrees and 7 degrees, or 4 degrees and 14 degrees, that would be 2:7. So how do I figure out? Ultimately, I need the measure of arc TS. I absolutely have to have that arc measure in order to take half of it to find TRS. Okay? Well, this is important. Because RS is a diameter, the measure of arc RS is 180 degrees. So let me write that down really quick because that is critically important. The measure of arc RS is 180 degrees. We go halfway around the circle, 180 degrees either direction. Now, I can set up an equation to figure out both the measure of RT and TS, although honestly it's just TS that I care about. And what I can do is I can say, well, I'm going to even do a let statement. Let the measure of RT be 2x, and let me let the measure of TS be 7x. This will guarantee that they're in a 2:7 ratio no matter what x is. All right? But then I can say, well, 2x plus 7x then is 180 degrees. That's going to give me 9x is equal to 180 degrees. And eventually that gives me x is equal to 20. Now, what did I really need? I needed the measure of TS. Well, that then, when x is 20, tells me the measure of angle TS, or arc TS, sorry, is 140 degrees. 140. And now I have everything I need because that means that the measure of angle TRS is 1/2 of 140 degrees, and that's 70 degrees. All right. But many different things we had to use there. The fact that we had a radius gave us that overall arc was 180 degrees. The 2:7 ratio meant we could break it up into 2x and 7x. That allows us to solve for the two arcs. Those would actually be 40 and 140. All right. And then finally, that relationship that says that the measure of the inscribed angle, TRS, is 1/2 of arc TS, allows us to finish off the problem. All right, let's take a look at one more problem. Explain why angle TWS must have the same measure as angle TRS. Also very important. Think about this a little bit. Pause the video if you need to. All right. Well, it's really kind of simple. They both intercept arc TS. And I hope you see that, right? Right, here's angle, always helpful to have it highlighted more. Here's angle TRS, and it intersects arc TS. Here's angle TWS, and it also intersects arc TS. And since they both intercept arc TS, they both must be 1/2 the measure of TS. All right? I mean, I could do this exceptionally formally. I could say, well, right, therefore the measure of angle TWS equals 1/2 the measure of arc TS, and the measure of angle TRS is 1/2 the measure of TS, and therefore the measure of angle TWS equals, there's my red, the measure of angle TRS. Watch that, yeah, there we are. And that would really be the substitution axiom of equality. When two quantities are equal to the same quantity, then they're equal to itself. And that makes sense. I mean, what was it? TS in the last case, at least, was 140, which meant that TRS would have to be 70 and TWS would have to be 70. All right, and that's another important thing. Inscribed angles that intercept the same arc have the same measure. That's a very important property of circles, all right? Great. Let's wrap up this lesson. So today, we learned an exceptionally important piece of terminology, and that's inscribed angle. An angle that has a vertex that lies on the circle and two rays that then intersect the circle. The other very, very important thing that we learned was about the measure of inscribed angles, and the fact that the measure of an inscribed angle will always be 1/2 of the measure of the arc that it intercepts. Never forget, of course, again, that the measure of an arc, the degree measure of an arc, not the length, not the physical length, but the number of degrees, is indicative of how far we've gone around the circle, and therefore it's measured by the central angle that intersects that arc. All right, we're going to work with inscribed angles much more in the next lesson. We're going to see other relationships that they have, other very important relationships. For now, I'd just like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.